Well, if you're watching this optional extra, it's because you want to know how to derive, or why t equals 2 pi root L over g for a simple pendulum, where L is the length of the pendulum and g is the gravitational field strength. Well, before we can derive that, there's a few tricks we need to remember, a few little bits and pieces. So first of all, do you remember what a radian is? Well, 1 radian, and you'll see why this is important later, but 1 radian, remember, is the angle subtended by an arc length equal to the radius. Do you remember that? So that's the definition of a radian. Generally, we can say the following. If I were to pick some angle, radian angle, not 1 radian, but some general angle theta, then it's true to say that the angle in radians times the radius is equal to whatever the arc length is, and I can actually write down theta r equals s. Now, if you're not familiar with that from maths, well, let's just try it out. And it kind of starts to make sense when you try it out once or twice. I mean, let's try it for 1 radian. If you plug in the angle 1 radian, well, 1 times r is equal to r, which is the arc length, which is the definition of a radian anyway. So that works. So it works when theta, this equation works when theta is equal to 1. Let's try it for 2 pi. That's the angle around a whole circle in radians. Well, 2 pi is the angle. So 2 pi times r equals, well, that's 2 pi r, and of course that's the circumference of a circle, so it's the arc length all the way around the circle. So that works. So you can sort of see, and if you think about that a bit, then it starts to make sense why that's always true. And that's going to be useful. Why, you might be wondering? Just let's note that a pendulum, if I imagine now a pendulum swinging from some point here, let's call it O, swinging back and forth, like this, backwards and forwards, then it's actually tracing out a circular arc. So that's why that becomes quite helpful when we're in the derivation later. Let's write in there an angle theta. This time the radius is the length of the string, the length of the pendulum, from the point where it's swinging about to the centre of mass of the bob. And so if we apply our rule here that we've just reminded ourselves of, then what we're saying here is that theta L equals S. So that's just the first thing to bear in mind before we actually get to this derivation. Well, the second thing to bear in mind is something called the small angle approximation. And now you also might be familiar with this in maths, but let's just see what's going on. The small angle approximation says that if theta is in radians, and it only works in radians, then we can actually say something quite surprising, that theta is roughly equal to sine theta. Are you serious? It's true. Well, if you don't believe me, grab your calculator. Now, this is only for small angles. So let's put here and small, and we'll decide what we mean by small in a minute. Well, let's take let's take 5 degrees. 5 degrees is pretty small, but that's not in radians. So if we convert that to radians, well, we'd need to plug it in our calculator. And we can calculate it. We can do, in radians, it would be 5 divided by 180 times pi. And if we write that as a decimal, we get 0.08726. So 5 degrees is 0.08726 radians. Well, if what I'm saying is true, if when the angle's in radians, theta and sine theta are about the same for small angles, then that means that sine of 5 degrees in radians should give us the same. So we need to find the sine of 0.08726. I've only done it to 4 significant figures there. But of course we have to make sure our calculator is in radians. If your calculator isn't in radians, do you know how to change it to radians? I hope so. If not, if you've got many people use a Casio, then you do a shift setup, and I'm sure you've done this lots of times, and then you can just pick out one of the options there. I think option 4 is for radians. And don't forget to go back to degrees, because that's a common problem when people get the wrong answers in questions, that they've gone from degrees to radians or radians to degrees and not changed back. Right, well, if you plug into your calculator the sine of 0.08726 when your calculator's in radians, you should get, and see if you agree, 0.08716. Wow, so, well, that's not far off. They are pretty close. I mean, they're the same to, they're good to how many, two significant figures. Then they start to deviate a little bit after that. Well, the question then is, you know, up to what angle is this okay? And when do they start to be too different? Well, the smaller the angle, the closer they get. The bigger the angle, the more they diverge. Well, this approximation is good for angles less than about 15 degrees. Yeah, once you get more than about 15 degrees, or 15 degrees, then the difference is more than 1%. You get an error of 1%, or it starts to increase from 1%. So if you want to get 1% error or less, then the angle needs to be less than 15 degrees. So small angles is what we're talking about there. Great, okay, so that's the second thing we have to know before we can actually do this derivation. So let's have a look at our pendulum. Okay, so here's our simple pendulum. And we can see that it is, in this position, displaced through an angle theta. Now I've done it much more than 15 degrees, but only for a nice clear diagram. But remember that a simple pendulum doesn't perform simple harmonic motion if the angle is, to an accuracy of better than 1%, if the angle gets bigger. So the bigger the angle, the less accurately it describes simple harmonic motion. Well, what is the displacement? Well, we've already talked about that. So if we sort of imagine there, the displacement is this arc here, this arc S. And the condition for simple harmonic motion, remember, is that the force, the restoring force, has to be proportional to the displacement and directed in the opposite direction. So here I've got a positive displacement, so the force must be acting in the negative direction. But what is the force? Well, the only force acting on our pendulum bob in this particular case is its weight. So I'm going to draw its weight straight down like that, bang. And that, of course, is mg, the mass of the bob times gravity. But of course, that is only part of that is acting towards the equilibrium, acting against the direction of the displacement. Well, so it's going to be the component in the direction of motion that we want, the component of that force in the direction of motion of the bob. What do I mean by that? Well, what I mean by that is that if I were to draw the two components of mg, one in its direction of motion, it would look pretty much like that. And then there's going to be a component perpendicular to its direction of motion, looking something like that, which is not going to have anything to do with it's not going to accelerate it. That perpendicular component won't accelerate the bob towards equilibrium. So it's only that one, only the one in the direction of motion that's important. Well, the next question, of course, is how does that component relate to mg? Well, if I just extend that line there, we can see that that angle is theta. So therefore, the component of the force, and let's just call it F, the force, the component that we want is F. Well, can you see that F will be mg sine theta? So that, it tells that now we've got at least some kind of expression for the force which is trying to move our oscillator, the bob, towards its equilibrium position. The other component of the weight doesn't matter at all. Right, great. So now I need a minus because let's put a minus in there because it's that when S is positive, the force is acting in the negative direction. So I shall just make a little bit of space to put in a minus, very important. And so F equals minus mg sine theta. So now we use the first little trick that for small theta, and remember I've done this quite big in my picture, but for small enough theta, usually 15 degrees or less for accuracy of 1% or better, then an error of 1% or better or less, then we know that sine theta is approximately theta, as long as theta is in radians. So now I can rewrite my equation, and I can rewrite it as f equals minus mg theta for small angles. Great, so we're getting somewhere pretty good now. Now the next thing to remember is our second little trick or the first one we did, which was just to realise that there's a connection between the angle, the displacement angle theta, and the displacement s. And if I draw on here the length of our oscillator, then you will see straight away what I'm talking about here. And what, of course, we're saying is that theta L is equal to our displacement s, which means that theta is s over L, and that means that I can actually write my new equation in an even more helpful way. I can write f equals minus mg s divided by L. Right, well, this is looking pretty good, because this is looking quite like what we're after. M is a constant, G is a constant, and L is a constant. So as long as the angle's small, then we've got our condition for simple harmonic motion. And I shall just write it in a slightly neater way. Let's put minus mg over L times s. Well, if that's the force, then we can do a similar thing. We can write a similar equation for acceleration. A equals f over m. So hopefully you are happy that A will be minus g over L times s. And then all we need to do is compare that to our defining equation for simple harmonic motion, which is A equals minus omega squared x, or in this case s, because our displacement is s. And so what do we get? Well, what we get is this wonderful thing that omega squared, the angular frequency squared, is equal to g over L. And from there we can pretty quickly get to where we're going. And I shall write down the fact that t is 2 pi over omega. And hopefully you could pause even, and you should be able to, from that position, by substituting in, come to what we're looking for, which is that t equals 2 pi root L over g. So there is our time period of a simple harmonic oscillator, only true to good accuracy when theta is small.